Klondike foothills, winter of 1897. While fellow miners raced to complete standard surface cabins before the killing cold, Scandinavian prospector Lars Nielsen was still digging, excavating deep into the frozen hillside, 12 miles from camp. His neighbors called it wasteful. They called him a fool. Why live in a hole in the ground when a proper log cabin had sheltered miners for decades? Then late March 1898 arrived, minus 60 degrees for 18 straight days, winds gusting to 80 miles per hour, the freeze that would test every shelter in the territory. Surface cabins failed. Interior temperatures plummeted to 25 degrees despite roaring stoves. Miners burned furniture to survive. Frost formed on interior walls. But Nielsen's dirt hole maintained 75 degrees while his neighbors' cabins froze. What did this immigrant prospector understand about surviving extreme cold that generations of frontier wisdom had missed? The creek beds around Bonanza and El Dorado had drawn thousands north, but the remote ridge country 12 miles from the nearest established camp remained largely untouched in the autumn of 1897. Here, scattered prospectors worked solitary claims on hillsides where permafrost ran 8 feet deep and spruce timber grew thick enough to supply a dozen cabins. The accepted wisdom among these isolated miners was simple and practical. Cut local logs, stack them into 8 by 10 foot rectangular shelters, lay sawmill planks for flooring, and install a small wood stove. The method had worked for frontier settlers across the Northern Territories for decades. Lars Nielsen had built exactly such a cabin on his first claim the previous year. The rectangular structure constructed of vertical spruce logs with simple chinking had seemed adequate during the moderate winter of 1896. Trade guides distributed at supply posts recommended this approach specifically for northern mining camps. The logic appeared sound. Timber was readily accessible, other miners used the design successfully in comparable conditions, and the construction required familiar skills that most prospectors possessed. But Nielsen's immigrant background had exposed him to different approaches to winter survival. Growing up in the farmlands of Minnesota after his family's arrival from Scandinavia, he had helped dig root cellars that extended 6 feet into the earth, creating storage spaces that remained consistently cool in summer and never froze solid in winter. The thick earth walls seemed to moderate temperature swings in ways that surprised him as a young man. His father had spoken of sod houses in the old country, structures built partially underground with thick earthen roofs that required minimal fuel to heat through the harshest Nordic winters. More recently, Nielsen had encountered Athabascan families during supply runs to the territorial trading posts. Their winter dwellings, he noticed, were not the teepees that many prospectors expected, but semi-subterranean structures built into hillsides with tunnel-like entrances that angled downward before rising into the main living space. When he inquired about this design, an elder explained that cold air was heavy and would settle in the lower tunnel, while warm air rose into the living area above. The principle seemed elegant and practical, though it contradicted everything Nielsen had learned about cabin construction. The failure of his first cabin during the severe cold snaps of late winter had crystallized his doubts about the conventional approach. Despite burning nearly 2 cords of wood per week, the interior temperature had dropped to 32 degrees on the coldest nights. Frost formed on the interior surfaces of the logs, and gaps opened between the timber as the wood contracted. The raised floor supported on shallow sill logs had shifted as frost penetrated the ground beneath, creating drafts that made the structure nearly uninhabitable. Other miners on nearby claims had experienced similar problems. Thomas Young's cabin, built on a flat bench overlooking his placer operation, had suffered roof damage when heavy snow combined with wind-driven accumulation exceeded the load capacity of his simple plank roof. The structure required emergency reinforcement in January, costing Young 3 days of mining work during the short daylight hours. Another prospector, working a claim 2 miles downstream, had reported interior temperatures dropping to 28 degrees despite continuous firing of his stove, forcing him to sleep in his clothes and boots. These observations, combined with Nielsen's background knowledge, led him to question whether the standard above-ground approach was appropriate for the extreme conditions of the Klondike region. The winters here were demonstrably harsher than those in Minnesota or even the northern Great Plains, with temperatures regularly reaching -50 degrees and wind exposure that seemed to strip heat from any structure built on the surface. When Nielsen announced his intention to excavate a shelter into the hillside rather than construct another surface cabin, the reaction from his neighbors was immediate and dismissive. Jim Carson, a mining camp foreman who had overseen the construction of dozens of conventional cabins throughout the mid-1890s, visited Nielsen's claim specifically to discourage the plan. "You're going to live like a badger," Carson declared, standing beside the small test excavation that Nielsen had begun. "A proper cabin's worked for every miner from here to Dawson City. Why complicate what's proven?" The criticism extended beyond practical concerns to questions of dignity and social standing. Mining camps operated on informal hierarchies where competence and conventional success earned respect. Building a dirt hole, as Carson termed it, suggested either desperation or an unwillingness to invest in proper shelter. Other miners expressed concerns that such unconventional behavior might attract unwanted attention from territorial authorities or undermine the camp's reputation among supply merchants who judged creditworthiness partly on the visible prosperity of mining operations. Nielsen's response was characteristically measured. He had calculated the fuel costs of his previous winter, approximately 6 cords of wood at considerable expense and labor, and observed that his conventional cabin had still failed to provide adequate comfort or safety. The risk of experimenting with an alternative approach seemed justified by the documented inadequacy of the standard method under actual conditions. The excavation work began in earnest in November, as other miners completed their conventional shelters. Nielsen selected a south-facing slope that would catch available winter sunlight and provide natural wind protection. The digging proceeded slowly through increasingly frozen ground, requiring careful attention to the angle of excavation and the structural integrity of the emerging chamber. By December, when the first serious cold arrived, Nielsen had created a basic underground space with dimensions roughly 10 feet by 8 feet, excavated approximately 8 feet into the hillside. The fundamental conflict was now established. On one side stood generations of frontier wisdom: build above ground, use familiar materials and methods, rely on proven techniques that had sheltered settlers across the northern territories. On the other side lay Nielsen's hypothesis that earth-sheltered construction, informed by both immigrant traditions and indigenous knowledge, could provide superior performance under extreme conditions. The approaching winter of 1897 would test both approaches under identical conditions, providing definitive evidence of which philosophy could better serve human survival in one of North America's harshest environments. The selection of the excavation site proved far more complex than Nielsen had initially anticipated. His first instinct had been to dig directly behind his existing claim structures, where the ground seemed most accessible. But a chance encounter with Wilson Kane, an Athabascan builder working on winter preparations at a nearby trading camp, redirected his entire approach. Kane examined Nielsen's proposed site with obvious skepticism. "Cold wind comes from northeast in deep winter," he explained, gesturing toward the exposed ridge where Nielsen had planned to dig. "You put house there. Wind hits you straight on. Better to find place where hill protects." Kane walked Nielsen around the claim, pointing out subtle features in the terrain that the prospector had never noticed. The south-facing slope, sheltered by a natural rise to the north and east, offered protection from the prevailing winter winds while capturing whatever limited sunlight penetrated the short winter days. More critically, Kane introduced Nielsen to the concept of the cold trap entrance. Traditional Athabascan winter houses, Kane explained, were accessed through tunnels that angled downward from the surface before rising into the main living space. "Cold air is heavy," he said, scraping a simple diagram in the frost with a stick. "It falls down into low place and stays there. Warm air goes up to where people live." The physics seemed counterintuitive to Nielsen, who had assumed that any opening would allow cold air to enter. But Kane's explanation made sense. Dense cold air would settle in the lower portion of the tunnel, creating a barrier that prevented it from reaching the living space above. The excavation technique itself required knowledge that Nielsen lacked. Eric Anderson, a Scandinavian homesteader who had established a small supply operation 2 miles from Nielsen's claim, had extensive experience with earth moving in frozen ground. Anderson had built semi-subterranean root cellars and sod houses on the northern Great Plains, where permafrost created similar challenges. "You cannot just dig like summer dirt," Anderson warned during his first visit to Nielsen's site. "Frozen ground breaks tools, makes crooked holes. You need fire." Anderson's method involved building small fires directly on the ground where excavation was planned, allowing the flames to thaw the permafrost in manageable sections. The process was painstakingly slow. Each fire could soften only 2 to 3 square feet of ground to a depth of 18 inches. But the technique allowed for precise control of the excavation boundaries and prevented the irregular, dangerous cave-ins that resulted from attacking frozen ground with picks and shovels alone. "In old country, we heat ground with coals. Dig little bit, heat again," Anderson explained. "Same work, but safe work." The depth of excavation became a crucial calculation. Surface cabins built on shallow foundations suffered from frost heave as the ground beneath them alternately froze and thawed, creating structural instability and gaps that allowed heat loss. But Anderson's experience suggested that excavating to the depth of permanent frost, approximately 8 feet in this region, would place the living space in ground that remained at a relatively constant temperature year-round. "Below the frost line, ground stays same," Anderson observed. "Maybe 32 degrees, maybe 28, but never changing up and down like surface." The excavation proceeded in calculated stages throughout December. Nielsen would build a small fire, allow it to burn for 4 to 6 hours, then remove the coals and dig out the softened earth before it could refreeze. The process yielded roughly 1 cubic yard of progress per day, requiring nearly 3 weeks to complete the main chamber. The tunnel entrance demanded even greater precision, as the angle had to be calculated to create the cold trap effect while remaining structurally sound. Kane returned periodically to inspect the work, offering adjustments to the tunnel design. The entrance needed to descend at a sharp angle for approximately 6 feet, then rise gradually into the main chamber. The total tunnel length stretched to nearly 10 feet, with the lowest point situated 2 feet below the level of the main floor. "Too steep, cold air bounces back up," Kane warned during one inspection. "Too gentle, cold air flows through like river." The final configuration created what amounted to a U-shaped air trap, with cold air pooling in the lowest section while warm air remained in the elevated living space. By early January, Nielsen could observe the immediate effects of these design decisions. Thomas Young's conventional cabin, situated on an exposed bench just 300 yards away, was subjected to the full force of the northeast winds that swept across the ridge. Young reported that his cabin's interior temperature dropped 5 degrees within an hour whenever the wind picked up, regardless of how vigorously he maintained his stove. The constant air infiltration through gaps in the log construction meant that Young was essentially heating the outdoors, requiring continuous feeding of his fire and consuming nearly 2 cords of wood per week. Nielsen's excavated chamber, protected by its hillside location, experienced no such temperature fluctuations. The earth surrounding the space maintained a steady temperature that, while still well below freezing, provided a stable baseline that required far less energy input to achieve comfortable interior conditions. More remarkably, the cold trap entrance functioned exactly as Kane had predicted. Nielsen could feel cold air flowing into the tunnel during frigid nights, but the temperature in the main chamber remained unaffected. The heavy cold air settled in the tunnel's low point and remained there, creating an invisible barrier that preserved the heat generated by Nielsen's small stove. The fuel efficiency became apparent within days. While Young and other surface cabin dwellers burned between 1 and 2 cords of wood per week to maintain barely tolerable interior temperatures, Nielsen's chamber required only 1/3 of a cord to achieve genuinely comfortable conditions. The excavated space, measuring 10 by 8 feet, reached interior temperatures of 60 degrees with minimal fuel input, compared to the 35 to 40 degree readings that Young recorded in his larger but conventionally constructed cabin. More subtle benefits emerged as the winter deepened. The structural stability of the excavated chamber eliminated the constant maintenance required for surface cabins, where frost heave and thermal expansion created ongoing problems with door alignment, window gaps, and floor levelness. Nielsen's excavation, carved directly into undisturbed permafrost, remained dimensionally stable regardless of surface weather conditions. The time and labor saved on repairs could be devoted to mining operations during the brief periods of winter daylight. By the end of January, the fundamental superiority of the site selection and orientation principles had been demonstrated under actual field conditions. The protected location, proper excavation depth, and cold trap entrance design had created a shelter that outperformed conventional construction by every measurable standard while requiring significantly less fuel and maintenance. The system worked not because of theoretical advantages, but because it addressed the specific challenges of extreme cold climate construction, with techniques developed through generations of practical experience. The raw excavated chamber, while properly sited and designed, remained little more than a hole in the ground until Nielsen addressed the critical challenge of creating a thermal envelope capable of retaining heat in extreme cold. The conventional approach used in surface cabins relied on single-thickness log walls with minimal insulation, a method that had proven inadequate during the previous winter's severe cold snaps. Nielsen's underground space demanded entirely different solutions for flooring, wall finishing, and roof construction. The floor presented the first technical challenge. Standard cabin construction placed wooden floors on sill logs that rested on the surface or in shallow excavations, creating air spaces beneath the living area that became conduits for heat loss. Eric Anderson had observed this problem repeatedly in his Great Plains homesteading experience. "Floor on stilts is like wearing boots with holes," he told Nielsen during a February visit to inspect the chamber's progress. "Cold comes up from below, warm goes down from above. Better to put floor right on solid ground." Anderson's solution involved leveling and compacting the excavated chamber floor directly against the undisturbed permafrost bench. This eliminated the air gap that plagued raised floors while taking advantage of the thermal mass of the frozen ground, which maintained a relatively constant temperature compared to the wildly fluctuating air temperatures above ground. The technique required careful grading to ensure proper drainage of any moisture that might accumulate, but created a foundation that would never shift, settle, or allow air infiltration. The wall system demanded more complex engineering. Single-thickness log construction, even with careful chinking, could not provide adequate insulation when subjected to temperature differentials of 90 degrees or more between interior and exterior conditions. Anderson introduced Nielsen to the double wall principle he had used in sod house construction on the plains. "In old country, we build wall inside wall," he explained. "Outside wall fights weather, inside wall holds heat. Space between them we fill with grass, moss, whatever stops air moving." Nielsen's implementation involved cutting spruce planks approximately 2 inches thick to line the interior surfaces of the excavated chamber. These inner walls were positioned roughly 1 foot from the earthen chamber walls, creating a cavity that could be packed with insulating material. The technique required substantial additional lumber, nearly 40 linear feet of planking for the chamber's perimeter, but provided a smooth, draft-free interior surface while creating space for insulation. The insulation material itself came from traditional knowledge that Anderson had learned from Scandinavian immigrants and refined through prairie experience. Moss, abundant in the surrounding forest, possessed natural properties that made it ideal for wall cavity insulation. When properly dried and packed, moss trapped air in countless tiny spaces while resisting compression and maintaining its insulating value even in damp conditions. Nielsen spent several days gathering and preparing sphagnum moss from nearby bog areas, drying it in small batches near his work fires, then packing it densely into the wall cavities. Wilson Kane contributed additional techniques from Athabascan winter house construction. Traditional earth-sheltered dwellings used layers of different materials to create thermal barriers, with each layer serving a specific function. Kane showed Nielsen how to mix dried moss with fine soil to create a denser insulation mass that would settle evenly and resist the air movement that could short-circuit the thermal barrier. Moss alone is good, but moss with dirt is better, Kane observed. Dirt stops air, moss stops cold. The roof construction presented the greatest structural challenge. The chamber's 10-foot span required load-bearing members capable of supporting not only their own weight, but also the substantial load of an earthen sod roof designed to provide thermal mass and weatherproofing. Conventional cabin roofs used lightweight construction with minimal insulation, an approach entirely unsuitable for Nielsen's requirements. Anderson's experience with sod house roofs provided the foundation for the solution. Load-bearing joists cut from local spruce logs, each approximately 8 inches in diameter, were positioned every 2 feet across the chamber's width. The joists extended into the earth walls on either side, distributing their load into the solid ground rather than relying on wall plates as conventional construction would require. This created a structural system capable of supporting enormous loads while maintaining the thermal integrity of the envelope. The roof covering itself represented a sophisticated layering system developed through generations of prairie construction experience. Over the structural joists, Anderson supervised the installation of a base layer of split planks to create a solid deck. Above this came approximately 6 inches of prairie grass or dried moss, followed by carefully cut sod blocks arranged in overlapping courses like shingles. The final thickness reached 14 inches, creating a roof system with thermal mass equivalent to several feet of earth. The sod cutting technique required specific knowledge that Anderson had perfected during his plains homesteading years. Proper sod blocks needed to be cut when the ground had adequate moisture content to bind the root systems together, but not so wet that they became unstable during handling. Each block measured roughly 12 inches by 8 inches by 4 inches thick, with the grass roots providing tensile strength that held the soil together. The blocks were laid with the grass side down against the plank decking, creating a living root layer that would eventually grow together into a continuous waterproof membrane. Construction of the envelope system extended through February and into early March. The double wall design with moss insulation created remarkable thermal performance that became apparent as soon as Nielsen lit his first fire in the completed chamber. With outside temperatures reaching -40 degrees, the interior space achieved 70 degrees while consuming only 1/4 quart of wood per week, a fuel efficiency that astounded observers familiar with conventional heating requirements. Thomas Young, whose surface cabin continued to struggle with interior temperatures in the 30s despite burning 2 to 3 cords weekly, visited Nielsen's chamber in early March and found the thermal performance almost unbelievable. "It's like summer in there," Young reported to other miners. "Lars is sitting in his shirt sleeves while my cabin's so cold I can see my breath indoors." The contrast demonstrated not just superior comfort, but fundamental differences in how the two envelope systems managed heat transfer. The structural stability of the envelope system proved equally impressive. While conventional cabins throughout the region experienced ongoing problems with settling foundations, shifting log joints, and thermal expansion gaps, Nielsen's chamber remained dimensionally stable. The undisturbed permafrost foundation eliminated frost heave problems, while the earth-sheltered walls were immune to the thermal cycling that plagued above-ground construction. More subtle benefits emerged as the system stabilized. The thermal mass of the thick earth roof moderated temperature swings, storing heat during the day and releasing it gradually at night. The moisture buffering capacity of the earth walls prevented the excessive dryness that plagued heated surface cabins, while the natural materials created indoor air quality superior to that found in conventional log structures, with their constant chinking repairs and draft problems. By mid-March, the completed envelope system had demonstrated performance characteristics that exceeded Nielsen's original expectations while validating the traditional knowledge that Anderson and Kane had contributed to its design. The chamber now functioned as an integrated thermal system rather than merely a heated space, achieving comfort and efficiency levels that conventional construction could not approach under identical conditions. The thermal envelope alone could not address the complex challenge of maintaining comfortable interior conditions while managing combustion, ventilation, and seasonal temperature variations. Standard mining cabin heating relied on oversized wood stoves designed for larger spaces and constructed without consideration for the unique airflow dynamics of underground structures. Nielsen's chamber demanded an entirely different approach to heating system design and air management. The stove selection process revealed fundamental flaws in conventional heating philosophy. Most miners purchased the largest wood stoves available, operating under the assumption that bigger fires produced more heat and therefore better comfort. Thomas Young's cabin, for example, contained a massive cast-iron stove with a 2-foot square firebox designed for heating spaces twice the size of his actual cabin. This oversized unit consumed enormous quantities of fuel while creating uneven heating patterns and dangerous overfire conditions that posed constant risks of carbon monoxide poisoning or structural fires. Eric Anderson's experience with heating small earth-sheltered spaces on the Great Plains had taught him different principles. Big stove in small room is like big horse pulling small cart, he explained to Nielsen during a March consultation. Horse gets tired, cart gets broken, nothing works right. Better to match stove size to room size, then room stays comfortable with less wood. Anderson recommended a compact cast iron unit with a 1-foot square firebox, roughly 1/4 the size of conventional mining cabin stoves. The smaller stove's efficiency became apparent immediately. Nielsen's chamber, measuring 10 by 8 feet, with an 8-foot ceiling, contained approximately 640 cubic feet of airspace. The compact stove could heat this volume to comfortable temperatures, while consuming only 1/5 the fuel required by oversized units in conventional cabins. More importantly, the properly sized unit eliminated the temperature swings that plagued cabins with oversized heating systems, where interiors alternated between stifling heat near the stove and bitter cold in distant corners. The combustion air management system required knowledge that neither Anderson nor Nielsen possessed initially. Wilson Kane's understanding of Athabascan winterhouse ventilation provided crucial guidance for managing airflow in underground structures. Traditional earth-sheltered dwellings used carefully designed air paths that supplied oxygen for combustion while preventing cold air infiltration and dangerous gas accumulation. Kane demonstrated the smoke hood principle that had been refined through generations of semi-subterranean dwelling construction. Rather than connecting the stove directly to a chimney pipe, traditional designs used an expanded chamber above the fire that collected combustion gases before channeling them through the flue. Fire makes smoke. Smoke needs place to gather before going up pipe, Kane explained, sketching the design with charcoal on a piece of bark. Smoke hood catches bad air, sends it outside, keeps good air inside. Nielsen's implementation involved constructing a stone and clay hood approximately 2 feet square positioned directly above the stove. The hood collected combustion products at the ceiling level, where they naturally accumulated due to their higher temperature, then channeled them through a 6-inch diameter clay flue pipe that extended through the earth roof. The system prevented the backdraft problems that plagued conventional cabin chimneys while ensuring complete removal of combustion gases from the living space. The flue design itself incorporated techniques that Kane had learned from traditional builders. Rather than using a straight vertical pipe that created strong updrafts and wasted heat, the traditional approach used a gently curving path that allowed maximum heat extraction from combustion gases before they escaped to the outside. Nielsen's flue curved horizontally for 3 feet within the earth roof before turning upward, creating a heat exchanger effect that captured additional thermal energy while maintaining adequate draft for proper combustion. Ventilation control became critical as winter deepened and the chamber's thermal performance exceeded expectations. The highly insulated space retained heat so effectively that small temperature adjustments could create significant comfort changes. Kane taught Nielsen to install an adjustable vent at the tunnel entrance that could regulate fresh air intake without compromising the cold trap effect. The vent consisted of a wooden slide mechanism that could restrict or open the tunnel entrance to control airflow rates. The seasonal adaptation challenge emerged as March brought warmer daytime temperatures, but continued nighttime cold. Nielsen discovered that his highly efficient heating system, designed for extreme winter conditions, could easily overheat the chamber during sunny spring days, when the earth roof absorbed solar energy. The problem required solutions that conventional cabin dwellers never faced, since their poorly insulated structures lost heat as rapidly as they gained it. Anderson's experience with seasonal management of sod houses provided the foundation for Nielsen's spring adaptations. In Old Country, sod house too warm in summer, too much earth-holding heat, Anderson observed during an April visit. We make holes in roof, let hot air out, cool air in. Same thing here, but careful not to let cold back in winter. The technique involved removing sections of the sod roof covering to expose the underlying earth mass to direct solar heating and creating small vents that could be opened or closed as conditions required. The thermal mass storage system represented Nielsen's most significant innovation beyond the traditional techniques he had learned. Observing that his chamber's temperature dropped approximately 8 degrees overnight when the fire died down, Nielsen installed a large flat stone slab measuring 3 feet by 4 feet by 4 inches thick directly beneath the stove location. The stone, quarried from a nearby ridge and carefully leveled into the chamber floor, functioned as a thermal battery that absorbed heat during active firing periods and radiated it slowly throughout the night. The hearthstone system required careful positioning and installation to maximize its effectiveness. The slab needed to be close enough to the stove to absorb radiant heat efficiently, but not so close that it created safety hazards or interfered with stove operation. Nielsen positioned the stone so that approximately half of its surface area lay directly beneath the stove, while the remainder extended into the room where it could radiate stored heat to the living space. The performance results exceeded every expectation. By late March, Nielsen's chamber maintained interior temperatures of 75 degrees, while outside conditions reached minus 50 degrees. Consuming only 1/5 of a cord of wood per week, the hearthstone system reduced overnight temperature drops from 8 degrees to less than 3 degrees, creating consistent comfort levels throughout the 24-hour cycle. Thomas Young's conventional cabin, by contrast, continued to struggle with interior temperatures in the 30s, despite burning 3 cords of wood weekly. More sophisticated benefits emerged as the heating system matured. The smoke hood and curved flue design eliminated the carbon monoxide problems that plagued conventional cabin heating, while the properly sized stove prevented the dangerous overfire conditions that had caused several cabin fires throughout the mining district. The seasonal ventilation adaptations allowed Nielsen to maintain comfortable conditions as spring temperatures began to warm, demonstrating that the system could function effectively across a wide range of external conditions. The air quality improvements proved equally significant. Conventional cabins, with their constant chinking repairs and draft problems, suffered from smoky interiors and dry air that caused respiratory irritation. Nielsen's chamber, with its controlled ventilation and proper combustion management, maintained fresh, comfortable air that supported better health and sleep quality during the long winter months when miners spent most of their time indoors. The most severe test of both conventional and alternative shelter systems arrived without warning in late March of 1898. A massive Arctic air mass, driven by unusual jet stream patterns, settled over the Klondike region and remained stationary for 18 consecutive days. Surface temperatures plummeted to minus 60 degrees, with sustained winds reaching 50 to 80 miles per hour that created wind chill conditions approaching minus 100 degrees. The prolonged extreme cold, combined with heavy snowfall that accumulated to depths of 6 feet, created survival conditions that exceeded anything the mining district had previously experienced. The conventional cabin failures began within the first 48 hours of the severe weather. Thomas Young's cabin, despite his frantic efforts to maintain continuous fires, experienced interior temperatures that dropped to 25 degrees, even with his oversized stove burning at maximum capacity. The extreme temperature differential between interior and exterior conditions caused his log walls to contract violently, opening gaps of up to 1/2 inch width between individual logs. These thermal cracks created wind-driven infiltration that made it impossible to maintain any meaningful interior warmth, regardless of fuel consumption rates. More catastrophic failures occurred throughout the district as the extreme conditions persisted. A cabin 3 miles from Nielsen's claim suffered complete structural collapse when frost heave, exacerbated by the deep temperature penetration, shifted its shallow foundation logs by more than 8 inches. The occupant, a prospector named Samuel Mitchell, was forced to abandon his shelter entirely and seek emergency refuge at a supply station 12 miles distant. Two other cabins experienced roof failures as the combination of heavy snow loads and extreme cold caused their supporting timbers to become brittle and crack under stress. The fuel consumption crisis proved equally devastating. Miners burning 3 to 4 cords of wood per week during normal cold periods found themselves requiring 6 to 8 cords to maintain barely survivable interior conditions. Many exhausted their entire winter wood supplies within a week of the extreme cold's arrival. James Harrison, whose claim lay 4 miles south of Nielsen's location, resorted to burning his cabin's interior furnishings, tool handles, and even portions of his sluice box equipment in desperate attempts to maintain life-supporting temperatures. His cabin's interior temperature never rose above 28 degrees despite these desperate measures. The wind factor created additional challenges that conventional construction could not address. The sustained high winds drove snow into microscopic gaps in log construction, creating interior snow accumulation that melted and refroze, further compromising structural integrity. Several cabins developed ice formations on interior walls within 10 feet of their fires, demonstrating the complete inadequacy of conventional heating and insulation systems under extreme conditions. Carbon monoxide poisoning became a serious risk as miners sealed gaps with rags and paper, reducing ventilation to dangerous levels while still failing to achieve adequate warmth. Nielsen's earth-sheltered chamber performed dramatically differently under identical conditions. The thick earth walls and properly designed thermal envelope maintained interior temperatures of 72 to 75 degrees throughout the entire 18-day extreme cold period. The underground location eliminated wind exposure entirely, while the thermal mass of the surrounding earth provided a stable temperature foundation that required minimal energy input to maintain comfortable conditions. Most remarkably, Nielsen's fuel consumption actually decreased slightly during the extreme weather, as the greater temperature differential between his warm chamber and the exterior cold improved the efficiency of his heating system. The structural stability advantages became most apparent during the windstorms. While surface cabins throughout the district suffered roof damage, wall separation, and foundation shifting, Nielsen's excavated chamber remained completely unaffected by surface weather conditions. The earth-sheltered construction was immune to wind loading, thermal expansion stresses, and frost heave problems that destroyed conventional structures. Nielsen continued his normal daily routines, including cooking, reading, and equipment maintenance, while miners in surface cabins struggled merely to survive. The rescue efforts that began after the first week of extreme weather revealed the extent of the performance differences. A supply party from the main mining camp, traveling on snowshoes to check on isolated prospectors, expected to find Nielsen's location abandoned or to discover a frozen corpse. Instead, they found him comfortable and well-fed, sitting in shirt sleeves beside his small stove while maintaining normal living conditions. The contrast with other locations they had visited was so dramatic that several rescue team members initially refused to believe Nielsen's chamber represented the same weather conditions they had observed elsewhere. Word of Nielsen's shelter performance spread rapidly through the mining community as the Klondike foothills, winter of 1897. While fellow miners raced to complete standard surface cabins before the killing cold, Scandinavian prospector Lars Nielsen was still digging, excavating deep into the frozen hillside, 12 miles from camp. His neighbors called it wasteful. They called him a fool. Why live in a hole in the ground when a proper log cabin had sheltered miners for decades? Then late March 1898 arrived, minus 60 degrees for 18 straight days, winds gusting to 80 miles per hour, the freeze that would test every shelter in the territory. Surface cabins failed. Interior temperatures plummeted to 25 degrees despite roaring stoves. Miners burned furniture to survive. Frost formed on interior walls. But Nielsen's dirt hole maintained 75 degrees while his neighbors' cabins froze. What did this immigrant prospector understand about surviving extreme cold that generations of frontier wisdom had missed? The creek beds around Bonanza and El Dorado had drawn thousands north, but the remote ridge country 12 miles from the nearest established camp remained largely untouched in the autumn of 1897. Here, scattered prospectors worked solitary claims on hillsides where permafrost ran 8 feet deep and spruce timber grew thick enough to supply a dozen cabins. The accepted wisdom among these isolated miners was simple and practical. Cut local logs, stack them into 8 by 10-foot rectangular shelters, lay sawmill planks for flooring, and install a small wood stove. The method had worked for frontier settlers across the Northern Territories for decades. Lars Nielsen had built exactly such a cabin on his first claim the previous year. The rectangular structure, constructed of vertical spruce logs with simple chinking, had seemed adequate during the moderate winter of 1896. Trade guides distributed at supply posts recommended this approach specifically for northern mining camps. The logic appeared sound. Timber was readily accessible, other miners used the design successfully in comparable conditions, and the construction required familiar skills that most prospectors possessed. But Nielsen's immigrant background had exposed him to different approaches to winter survival. Growing up in the farmlands of Minnesota after his family's arrival from Scandinavia, he had helped dig root cellars that extended 6 feet into the earth, creating storage spaces that remained consistently cool in summer and never froze solid in winter. The thick earth walls seemed to moderate temperature swings in ways that surprised him as a young man. His father had spoken of sod houses in the old country, structures built partially underground with thick earthen roofs that required minimal fuel to heat through the harshest Nordic winters. More recently, Nielsen had encountered Athabascan families during supply runs to the territorial trading posts. Their winter dwellings, he noticed, were not the types that many prospectors expected, but semi-subterranean structures built into hillsides with tunnel-like entrances that angled downward before rising into the main living space. When he inquired about this design, an elder explained that cold air was heavy and would settle in the lower tunnel, while warm air rose into the living area above. The principle seemed elegant and practical, though it contradicted everything Nielsen had learned about cabin construction. The failure of his first cabin during the severe cold snaps of late winter had crystallized his doubts about the conventional approach. Despite burning nearly 2 cords of wood per week, the interior temperature had dropped to 32 degrees on the coldest nights. Frost formed on the interior surfaces of the logs, and gaps opened between the timber as the wood contracted.